Hello everyone and welcome to our calculus notes for section 3.4. Our first topic we're going to discuss is something called concavity. And we're going to let a function be differentiable on an open interval I, and we're going to say the graph of f is concave upward on I if f prime is increasing on the interval. So concave upward, you've dealt with this before in dealing with something like a parabola. It would look something like this. So on the interval that I've drawn, this thing is concave upward. And what you've learned before is that this graph opens up. So graphically we can see that it opens up. We can almost think about if we were to pour water into this guy, okay, the water would actually fill up. So it holds water there. Now, what we want to do is talk about this a little more analytically in terms of the derivative. Now, what's happening here, if a graph is concave up on an interval, the derivative is continuously increasing on that interval. Okay, so we could just take a couple points right here and let's talk about the derivative of the function at each of these points. Okay, now we know the derivative is the slope of the tangent line. Okay, so we're going to draw some tangent lines here. Okay, now this one, that's fairly steep and negative. Okay, if we were to draw the tangent line through this point, notice here that it is still negative, but it's not quite as steep. So we would say that this derivative at this point is larger, or has a higher value, than this derivative right here. Okay. Now if we look right here, this is our minimum, and we knew that the derivative is 0, so we have our horizontal tangent line. So 0 is larger than a negative number. So you can see so far our derivative is increasing. Okay. The derivative at this point is the slope of this tangent line right here. And we can see now that this tangent line is positive, which is larger than 0, so the derivative is still increasing. And then if we look at the derivative here, we'd get this tangent line. And you can see that this graph is steeper than this graph, so therefore this one has a higher slope, meaning the derivative is still increasing on that entire interval. Now one thing to notice is the graph lies above all of its tangent lines on the interval. So you can see here these tangent lines are all below the graph, and the graph is above all those tangent lines. And what we're going to learn today is the way we're going to be able to find this is that the second derivative is going to be positive for all the x's on the interval. So we think about this as if the derivative is continuously increasing, well, the second derivative tells us what the first derivative is doing. And so if the second derivative is positive, that means that the first derivative is increasing. Okay, so that's kind of the idea of what's going on here. Concave downwards is the same type of idea, except now our graph is opening down. Okay, so visually that's what it looks like. And our derivative is constantly decreasing. So we could pick some points on our interval again. And to really view the derivative, we could see our tangent line here. Okay, so that's very steep, positive. Still positive, not quite as steep. Here we would get 0. Here it's negative. Okay, and here it's very steep and negative. So you can see that our derivative was a very high positive number, a little bit lower to 0 to negative to a very low negative number. And so you can see that the derivative, f prime, is decreasing on the interval. Now, graphically, if we were to think about the water, if we poured water on here, right, the water would just all spill right on out. Okay, so that's how we can think about this graphically. So what happens here is the graph is going to lie below all of its tangent lines. So you can see here that the graph is completely underneath all the tangent lines. And it turns out now that the second derivative is negative for all the x's on the interval. So in our first example, it says determine the open intervals on which the graph of f is concave upward or downward. Now, we can look at this graphically, and you can see here we kind of have this sloping down type of effect here, and then this curving up type of effect here. And so we might assume that it's concave down on this interval and concave up on this interval. Now, if we tried our whole water trick, if I were to pour water into this interval that stopped there, the water would just run right out. So the water trick doesn't always work to determine whether something is concave up or concave down. What will always work is using the second derivative to determine the concavity. So what we want to do is locate the x values for which f double prime of x equals 0 or does not exist. Okay, we're going to use these x values as our testing intervals. And then we want to test the sign of f double prime of x, or the second derivative, in each of the testing intervals. Now we also want to use x values where f is not continuous or f prime does not exist. So there's a couple little extra things there. But first off, we need to find that second derivative. Okay, so first off, we have to find our first derivative. That's just 3x squared plus 3. And then we go ahead and find our second derivative by taking the derivative of the first. So power rule, we get 6x and then plus 0. So we found our second derivative, and what we want to do is find where the second derivative equals 0 or does not exist. You can see it exists on the whole number line, so we don't need to worry about that. And we can see that it equals 0 when x equals 0. So 0 really becomes our marker here for our concavity tests. We're going to put 0 right here. So we're going to have an interval to the left of this, which will be negative infinity to 0. And then on the right of this, it'll be 0 to infinity. Alright, so next we want to pick test values that fit in this interval. So I'm just going to try f double prime of -1 here, and here we can try f double prime of 1. So keep it simple, it just has to fall in the interval. So if we were to plug -1 into our second derivative here, we would get 6 times -1, which is -6. And what we're interested in is the sign of f double prime of x, and the sign is negative. Okay. For this one, f double prime of 1, so we're going to plug 1 into our second derivative, so 6 times 1 is 6. And what we're concerned about is the sign, and this is positive. So the conclusion is, if the second derivative is negative on an interval, we call this concave down. And if the second derivative is positive on an interval, we call this concave up. So what this means is, if the second derivative is negative, it means the first derivative is always decreasing on this interval. And if the second derivative is positive, the first derivative is increasing on this interval, so we get concave down and concave up. Our concave down interval would be negative infinity and 0, and we write it as an open interval. And then it's going to be concave up from 0 to infinity. Okay? So in our graph, we would see here that this all is concave down. And we can see here that's true because f double prime of x is less than 0 here. And then on this interval, from 0 to positive infinity, we can see it's concave up because f double prime of x is greater than 0, or it's positive. Okay, now we're going to use some abbreviations here just to make this a little faster. So concave down, we're just going to write as CD, concave down. And then concave up, I'm just going to write CU for concave up. All right, we're going to move on to our next example here. And I want you to try this one on your own. Welcome back. So hopefully you're able to find your first derivative. Okay, and then move on to your second derivative. Here you had to use the quotient rule. And it gets a little bit messy, so to clean these up, we factored out some stuff, and we come out to something like this. Okay, so if you're still struggling with how to find those first derivatives or second derivatives, please come see me for some extra help. Then the new stuff today was applying, just setting the second derivative equal to 0, so that would be where the numerator equals 0, and then we can see here that we get x equals 1 or negative 1. Now those guys end up being our testing intervals here at negative 1 and 1. And so you can see we picked the intervals right here. We picked test values in those intervals. Your test values may be different, but the signs of the second derivative is what we're really concerned about. And so you should have gotten concave up on the interval negative infinity to 1, concave down on negative 1 to 1, and concave up from 1 to infinity. And we can see here on the graph that the first derivative is increasing all along this interval, and then we can see the first derivative is decreasing on this interval, and then the first derivative is increasing on this interval. So we can see concave up, concave down to concave up. So that has been how to find concavity of a function on an interval.